Okay, so we saw, so far we've been looking only at regression, which is trying to fit those lines on those points and so on. So basically trying to predict a continuous value. And now we're going to look at classification. But we're going to look at classification using this classifier, which is called logistic regression, which is actually inside a regression. And the idea here is that we're both going to look at the difference, conceptual difference between classification and regression, but also see how they are related and how we can use regression for classification. We're going to start by looking at the goal of classification, looking at linear separability, and then we're going to see how we can use logistic regression to classify any data that we're going to meet based on the data that we have for training. So this is an example of a data set for measurements in cells. So these are for the expression of some genes in cells, and the cells are classified into two different classes. The blue one is normal, the class of normal cells. The red one is the class of tumor cells, so cancer cells. And we can say that this set of data is linearly separable because we have a straight line, or in general, if we have n dimensions, we have an hyperplane in that dimensional space that can split the data into the classes that we have. So these two classes, with these two classes, these data points form a linearly separable set. So this means that we can build a classifier that can, in theory, correctly classify this data just by finding the right line to split the point. We can use a set of hypotheses that separates the point with straight hyperplanes, a line in two dimensions, a plane in three dimensions, and so on. This frontier here, in this case, it's a linear discriminant because the discriminant is a linear combination of our features. In two dimensions, it's a line. In three dimensions, a plane. In four dimensions, a hyperplane, and so on. If this does not happen, so this is an example also from the same data set but using two different features, we see that there is no straight line here that can separate these classes, so these are not linearly separable. Now, in the regression, we defined the line that we wanted to use to approximate our points by the epsilon value as some set of parameters multiplied by the x and another parameter added here. So if we have a straight line in two dimensions, it will have simply two parameters, epsilon equals to θ1x plus θ2. In classification, we don't want just the line, we also need to know in which side each of the classes is. So there is one positive side of the line, one negative side, or the discriminant in general. I'm using a line here because it's easier to show things in two dimensions, but in general it can be for any number of dimensions. So for n dimensions we have a hyperplane, and we need to define which side is class 1, which side is class 0 or class minus 1. The label is not very important. So what we can do is we can define this hyperplane using a vector of parameters that is perpendicular to the plane. And so everything that is on the plane, the value of this expression, which is that perpendicular vector multiplied by the vector of features plus this additional parameter, is 0 on the plane. It will be negative on the side opposite to the one pointed to by this vector, and positive on the same side. So the idea in three dimensions would be something like this. We have our data points here. We have a plane that separates them, and the orientation of the plane is defined by this perpendicular vector, and the height of the plane is defined by that extra parameter there. So in the plane, the value of this function is 0. on one side of the plane it will be positive and increasing, on the other side of the plane it will be negative and decrease as the further we get from the plane. So this way we can split the space into two classes and have one on one side, the other on the other. So given this set of hypotheses, so we have, this is our model that describes the set of all possible hyperplanes. How can we find the best hypothesis, the one that splits our data the best? So we need to instantiate those parameters in a way that we can separate, we can find the discriminants. So let's start by doing this the wrong way. The reason for doing this the wrong way is not for you to do this the wrong way, obviously, but for us to understand the big difference between regression and classification and how we need to think differently when we're solving these kinds of problems. So let's say we have this is our model, we have these parameters W here. We need to find the best parameters, and we know that expression is positive on one side of the hyperplane and negative on the other. So if we label our data as say -1 and +1, depending on the class they fall into, we can try to fit our hyperplane so that the negative ones will be on the side of the labels with -1, and the positive side of the hyperplane will be on the side of the +1. And we can try to minimize this difference, for example, by using the same cost function that we use for regression. We can use this quadratic error, in which we have the value of this expression at each point, and we see the difference between this value and the label of the class, which is +1 for one class, -1 for the other. So this will try to put the plane in a way that gets all the negative ones on one side, or the positives on the other. So this is easy to do. We take our data. So in this case, we have these two genes, carbonic anhydrase and guanylate cyclase. These two genes, the activity of two genes are the features. So the X vector has these two values, and this is what we are representing in this chart. So the two genes here, and the label, what we want to predict, is the class for each cell, whether it's a normal cell or a cancer cell. So here we have the data. We have a cancer cell is labeled 1 here, and the tumor cell is labeled 0, but we can then change that to 1 and -1, and this will be our two classes. So now we have all these values here, and it's useful to get them in a reasonable range. We saw that with the GDP and life expectancy problem, and now we're going to look at this a bit more formally, and these are the two most used ways of rescaling the features. Normalization puts everything, makes a linear transformation on the values and puts them between 0 and 1. So basically, for each point X, we subtract the minimum value of that feature for all our data sets, and then divide by the range, so maximum minus the minimum. This way, all the values for our data will fall within the range of 0 to 1. This is good if you have a more or less random distribution, so you rescale everything and it falls between 0 and 1. It's not very good if you have a distribution that is concentrated somewhere and then there are a few outliers, because when you reduce everything to between 0 and 1, most of the data will now fall into a very short range, and then you have a few outliers at 0 and 1. The alternative is to use standardization. Standardization converts your set of values into a set of values that has a mean value of 0 and a standard deviation of 1. So what you do is you divide by the mean of all the values, by the average of all the values, and divide by the standard deviation of all the values. This is good if you have a more or less Gaussian distribution. Even if you have some outliers, it's okay, there will still be outliers, but you get your distribution around 0 and with a standard deviation of 1. So we're going to do this, we're going to do standardization on our data. We load the data, we separate the epsilon and the x values, and we're going to standardize the x values. Note that it's not, in this case, it will not be correct to standardize the epsilon values, because the epsilon values, what we want to predict, are just these labels, 0 and 1. So they are not actually continuous values. We're not going to change them like this. What we're going to standardize is just the features. So these gene activation measurements here in the X part. So we have the epsilon values are the last column of the matrix. The X value is everything up to the last column. This you don't need to memorize this notation here. The idea is just to show you that it's easy to manipulate these matrices with NumPy. So basically what we're saying here is that from the matrix we want all the rows. This column means all the rows. And we want the last column, the index -1, you're counting from the end, but we want it as a column. So we give it as a list of values, and it will not lose that dimension, because the last column is just a vector with a dimension of 1, but if you specify like this, you get a matrix with a single column. You still retain the same dimension. And here you want all the rows and all the columns up to the last one. So everything from the first one to the last, excluding the last one. Now, to do this standardization, we just compute the mean of the columns on the mean of the X matrix on the direction of the rows. So we get one mean value for each column, and we do the same for the standard deviation, and we just divide. So when you do this kind of operations with the NumPy matrices, you can broadcast operations. So if you have a matrix and a vector, you can divide each row of the matrix by all the values on the vector and on the same order. This means you don't need to loop, to use for loops or something like that for this operation. However, this is not something that is easy to learn just by looking at it. You'll do it in practice a few times, and then you'll get the hang of it. But anyway, we're loading the data, and we're standardizing the features, not the class labels. It's not reasonable to standardize the class labels, because they just indicate which class each cell belongs to. Now, we can simplify this expression, and you'll see this in many textbooks, by changing our feature values and adding a value of 1 to the vector. So at present, this vector x has two values, the two activations of the two genes. So if we want to compute the epsilon value for on which side of our hyperplane the point is, we need to multiply to compute the inner product of the vector of parameters by the vector of features, and then add this constant to determine where the plane will be, if higher or lower. But what we can do is to simplify this expression to a simple dot product, to a simple inner product between these vectors, by putting this W0 inside the parameter vector. This is another parameter that we need, and adding a 1 to the feature vector, because then it will be the same thing. The dot product is simply the multiplication and then summing everything. So this is what we can do here. We can use all the parameters in this vector and then add W0. We do the same thing for the features, all the feature values, and put 1 at the end. And now this expression reduces to just the inner product here. So we can do this like this. We create a new expanded matrix with the original number of rows, 1 additional column, and then create this matrix filled with 1. So this 1 function returns a matrix filled with 1. And then we just copy the original matrix to everything except the last column. And now we have the final parameter for our model will be at the end. Now we can measure the error. So we receive a vector with all the parameters. We receive a matrix with all the features and the epsilon values, which are the classes that we want to predict. And if we're using this quadratic error, we can measure the errors by simply the dot product, so the inner product between the matrix and the coefficient. The trick here, you have to remember, algebra is the orientation of the vector. So if the matrix has each example in a row and have 3 columns, and your vector has 3 values, then you need to have the vector in column to put it there, and we can do it like this. We create a matrix with 1 column, we fill in the vectors there, and then we multiply. But this is just a detail. Usually you're not going to do this kind of operation by hand. This is just to show you how things are working inside. But if you do this, what I usually do is I experiment. If I get an error or something that makes no sense, I change the direction, because I never remember which one has to be the column or the row. But it's easy to experiment, or just look online which one needs to be what. And then once we have all the values from this dot product, so all the epsilon values predicted by our function with those parameters, we can subtract those from the actual epsilon values, the class labels that we have in our data. The only change here is that since our data has class values of 0 and 1, we need to change that to -1, 1, and so this is just what the computation I'm doing here. So if this is 0, we have 2 times 0 minus 1, it becomes -1. If it's 1, it's 2 times 1 minus 1, so it becomes 1. But this is just to measure the error, the positive side and the negative side. So we can do this by using this minimize function. This minimize function from SciPy will receive a function of the cost of the error and try to find the best coefficients for minimizing the value returned by that function. So it's sort of like solver in Excel or something like that. And so we get our data, and then we obtain the values for our hyperplane, for our discriminant, and we plot. So what we get as a result is this. You see, we used a quadratic error cost function. We have positive one side, negative on the other, but then the line passes right through here instead of going between the 2 classes. So we have some errors here which we should not have, because it should be easy to separate the 2. And the reason for this is that since we are using a quadratic error, these points far away here are pulling the line to this side, because we're trying to place the line as best between this set and to minimize all these differences. But this is not what we want here. If we were doing regression, then points that are very far from the line are bad, because this means our hypothesis is not fitting the data correctly. So when we use a quadratic error, we are trying to put the line as close as possible to all the points. But when we're doing classification, these are actually the least interesting points. We don't really care about these, because if we put the line here, the only thing that matters are these ones that are here. These are the ones that are critical to separate the 2 sets. The ones that are far away, we don't really care about them, because they're already in the right place, so it doesn't matter. So this is a very big difference between regression and classification. When you're trying to predict a continuous value, you're trying to fit your hypothesis so that it goes as close as possible to all those values you're trying to predict. When you're classifying, you're trying to split your data into different sets, and this means that we want to find some line that cuts the different classes. And so in this case, it's not a problem if you have something on the right side that is far away from the line. The only problem are those that are at the frontier, because those are the ones that determine where the line must cross. So, least mean squares, it makes sense in regression. It's the maximum likelihood solution for assuming the error on the epsilon value, but we should not do this in classification because of this fundamental difference between regression and classification. In classification, we do not want to approximate the point, we want to cut the data, the set, into the different categories. So let's look at logistic regression and how we can solve this problem better. Let's assume that there is some function that tells us the probability given the features, for example, in our example here, the gene activities, the probability of the class being class 1. For example, given the gene activities, the probability of being a tumor cell. If this function exists, we want to try to approximate it in order to classify our data. So we're going to assume that this function exists, and we're going to place our discriminants at the line or the frontier in which, given the feature, the probability of belonging to class 1, for example being a tumor cell, is the same as belonging to class 0. So everything that has a higher probability for one class belongs to that class, everything that has a higher probability for the other class belongs to the other class, and right in the middle, where the probabilities are the same, this is where we draw the line to distinguish the two classes. So since we are assuming that this is a probability, this function should range between 0 and 1, because probabilities fall between 0 and 1. Also, we know that if we have a discriminant somewhere, we want this, for example, this hyperplane, where the value is 0 at the hyperplane, the value of epsilon. So, value 0, when the two probabilities are the same, we can use the logarithm here of the probability of belonging to the class and the probability of belonging to the other class, which is 1 minus the probability of belonging to this class. And if we take this, divide one by the other, and we take the logarithm, when they are the same, this is 1, the logarithm of 1 is 0. When 1 is the one above, so the probability of class 1 is higher, this is positive, and when the probability of class 0 is higher, this is negative. So this way, we can approximate, we can compute the parameters for the hyperplane that will give us the same result, because this logarithm will range from minus infinity to infinity. The function here ranges from 0 to 1, and the value that we get when we multiply this vector that describes the hyperplane by the features and add that constant will be higher, positive, or negative, depending on where the point is relative to the plane. So this is basically the conditions that we want. We want a function that is a probability, and we want to define this hyperplane that cuts at the frontier where the probabilities are the same for the two classes. If we solve this equation, we get the expression for our function. So far we didn't know exactly how our function would be, but if we want this hyperplane and we have these conditions, then our function is something like this: 1 over 1 plus e raised to the value, to this value here, the epsilon value that we had before. And this is the logistic function. So this is the shape of the function. It goes between 0 and 1, as a probability function should be, but it has this step here around 0, and then it saturates close to 1 and close to minus 1. And this can give us an intuitive idea of why this is much better than the quadratic function. The quadratic function that we used was growing arbitrarily large away from the discriminant. So points that were away from the discriminant were actually counting more than those that were close to the frontier. The logistic function doesn't do that. It just levels out. So everything that is, as long as they're on the right side, then it doesn't matter, because they all count the same for one side and the other of the frontier. And we no longer have that effect of points that are far away pulling the frontier out of the place where it should be. So now we're going to find the best parameters by maximum likelihood. Remember, the likelihood of a set of parameters or a given hypothesis is the estimated probability of the data that we have, assuming that the hypothesis is true. This is, we have to think of it backwards, because neither our hypothesis nor the parameters are random variables. We are choosing them to adjust the model. But the data that we have, we are assuming that it's a random sample from some universe, which we're trying to model with our model. So, assuming that our function is giving the probability of the class being 1 given the features, so we give the features to the function and it tells us what the probability is that the cell is a tumor cell, we can compute the likelihood of the parameters by computing the probability of the data. And the probability of the data is the product of either the value of the function if the data point belongs to category 1, class 1, or 1 minus the value of the function if the point belongs to class 0, because that would be the probability of belonging to class 0. That's 1 minus the probability of belonging to class 1. And that's easy to do if we simply raise the probability to the value of the class. because if the class is 0, then this is 1 and will not do anything on the product, and if the class is 1, then we use the probability that we have here. And the same thing here, just using 1 minus the value of the class. So that's the probability of the data given the hypothesis. We can take the logarithm because we want to maximize this, and the maximum is the same if we take the logarithm. It simplifies the expression, and basically what we end up with is with something similar to what we saw in the linear regression. It's not a quadratic error. It now uses these logarithms of the function, but the idea is that we are minimizing this value. This is the logistic loss, or the cross entropy, and this g here is this logistic function that we have. So just apply this formula. The class of each point multiplied by the logarithm of the g function, plus 1 minus the class of the point multiplied by 1 minus the logarithm of 1 minus the value of the function. And the reason for this is that if the point belongs to class 1, then this is the probability of belonging to class 1. If the point belongs to class 0, then this is the probability of belonging to class 0. Okay? So we are doing this 1 minus because of that. Okay, so let's see an example. This is a function just to compute a logistic function. 1 over this, 1 plus e raised to minus 1 times x. And then we create the cost function which computes this expression here. So basically we get the parameters for our hyperplane, the features of our data set, and the class labels that we're trying to predict. And now we do the multiplication of our vector of parameters by the matrix of features. So we get all the values of this term here. So this is basically the values that we obtained from that hyperplane equation. And now we do the logarithm for those that belong to class 1, for those that belong to class 0, and then we compute the average value of this sum and change the sign here. So this is what we want to maximize, this is what we want to minimize, we just have a different sign. Okay, so now we do the minimization of this. We can use the same function, minimize function. We are just not using the quadratic error, we are just using this logistic loss, and now we get something that looks a lot better. Okay? So we change this quadratic function that tries to bring the line closer to those that are further away. We change it to the logistic function that doesn't really care if the point is much further away or not, and now it's more important to look at the points that are close to the frontier. But we are still doing a regression. The thing is that we are doing a regression to a hypothetical function of the probabilities of belonging to some class. And then we take the line where the probability is the same for one side and the other, and that would be the discriminant for the classification. If we have a set that is not linearly separable, we can still use logistic regression, but of course the straight line will not be able to distinguish correctly between the two classes. So we are using this equation for a hyperplane here, and this is a linear expression on the features, so we can only split things that can be split linearly with a straight hyperplane. If we are in this dimension, this cannot be split with a straight line. There is no function that we can find, no set of parameters that can really tell these two classes apart without error, because we cannot do curved lines here with that model. But we saw the trick for solving this. We still use a linear classifier, so we still have a linear expression for distinguishing the classes, but we can do a non-linear transformation of our data set and do this linear classification on a higher dimension after this transformation. So this is what we're doing here. We can expand these features by creating, for example, with an additional feature that is the product of the two original ones. So we are transforming the data in a way that is non-linear because it now multiplies each of the two original features, and we create a new matrix with an additional column we copy the original matrix to the beginning, and then we add a new column that is just the product of the values of the original data. So we don't really have new data. This is the same data, but now we are extending to higher dimensions with a nonlinear transformation. And now we can do logistic regression. We're going to do it the way you're going to do it also in practice, which is not this way by hand, by creating the cost functions and minimizing. This is not very optimized. We're going to use from scikit-learn the logistic regression class. We're going to create an object of this class. This is a regularization term. We're going to talk a bit more about that later, but basically in scikit-learn, we'll see why when we look at support vector machines, but in scikit-learn the standard, the convention is that the regularization term has a lower effect the higher it is. So actually this is a sort of a lambda like in ridge regression, but it's taken 1 over this value. So if this value is very high, regularization is very low. So we're not using regularization here. This is just a tolerance value to stop the optimization when finding the parameters. But basically we use the object of logistic regression and we do a fit for our data, and it computes the model. The thing is that we're not fitting with the original data, because if we did that we would get a linear classifier, and we cannot separate this linear in these dimensions. We are doing this linearly but with the expanded data. So what we're doing is actually this. We took the two X features, we added the third one, so now our features are in 3 dimensions. But since it's a nonlinear transformation, our features are now spread in a curved surface in 3 dimensions. If we cut this curved surface with a straight plane in 3 dimensions, and then we project it back, the intersection between the two is now something that cannot see this very well. Well, you should see. It's very hard to see, but you probably see that this is slightly darker here below and a bit lighter above. So this is the curve that we obtain when we intersect again. So basically it's the same idea that we saw with the polynomial curve. We are using a linear model, but we are using the linear model in 3 dimensions on a nonlinear transformation of our data, which means that when we go back to the original 2 dimensions, the cutting plane, the plane cuts at a curve in this original dimension. And now we can do this more. We can expand more terms. As long as the transformation is non-linear, this works. Note that it's pointless to have here something that is, for example, 2 times x2, because that would be a linear transformation, and if we go to higher dimensions with linear transformations, we still have everything on the same plane, and we cannot cut it anyway. So what we're doing is we are twisting the surface in higher dimensions, so that when we cut with a straight plane, we get something that is curved in the original space. And we can do this higher and higher and arbitrarily. So here now we have a very a more twisted curve, and eventually we'll start with the problem of overfitting too. So whether we're dealing with regression or classification, we can usually make the model arbitrarily flexible, decrease the error in the training set, but at some point we are increasing the error outside the training set and things are getting worse. So this is the same problem of overfitting. So summing up, we saw this constant of linear separability. This will be important because usually we're going to use linear classifiers. But the thing is that just because the classifier is linear in the dimension it is using our data, it doesn't mean that we can only split things that are linearly separable, because we can always transform our data non-linearly to overcome that problem. We saw how the idea of least mean squares, of fitting the line as close together to the point, does not work well in classification, because in classification we are doing something different. We try to find a way to cut the data into points, but still we can use regression. So in the case of logistic regression, instead of trying to predict the class as a continuous value. We are trying to predict the probability of belonging to the class, and then we choose a cutting point where we separate the two sets. So next lecture we're going to look at overfitting in classification and see a bit better how we can estimate the true error. Remember that we use that validation set, but that gives us only one sample at each time. So we'll improve that a bit, and then we'll see how to solve overfitting in logistic regression. So for logistic regression, I recommend that you read these sections of Bishop.